Hey guys, welcome to video 47. Today's topic is depletion mode MOSFETs. On the left hand side of the screen we've got the schematic symbols for the two types, the N channel and P channel. And just like the other transistors we've talked about, you're going to see way more N channel devices used in the real world. So that's what we're going to concentrate on today. In the center we've got the cross section for a typical discrete depletion mode MOSFET. This is an N channel device. Notice we've got a continuous conductive N channel from drain to source, so this is a normally on device. Now I'm going to try and give a brief explanation of how this works. Just remember, since we've got a PN junction, we're going to have a depletion region formed, and I'm just going to show it on the N side here. And what happens is when we apply voltage across the device, we're normally going to ground the source. We're going to get current flow down through the transistor, and as we increase the voltage from drain to source, we're going to increase the voltage gradient, which stretches the depletion region up and out. And eventually we'll reach enough drain current and voltage from drain to source that we're going to pinch off the channel and get a relatively constant drain current regardless of the voltage applied. Now, if we initially apply a negative gate voltage with respect to the source, we're going to increase the size of the depletion region initially so we reach pinch off or saturation sooner. And if we apply a positive voltage at the gate with respect to the source, we're going to shrink the size of the initial depletion region, so it takes longer to reach saturation or pinch off. All right, the gist of the whole thing is that we can operate this device either in this second quadrant, which would be the depletion mode, or the first quadrant, which technically would be an enhancement mode operation. But it has the same equation describing the drain current versus VGS as the JFET, and here it is. So we've got IDSS, which is the drain current with 0 VGS, and VGS off, which is the vertex of this parabola, that is the gate to source voltage required to cause pinch off with no voltage applied from drain to source. So what we see here is that the depletion mode MOSFET has some characteristics that are similar to JFETs, in particular the transconductance equation, and some characteristics that are similar to enhancement mode MOSFETs. Keep in mind that for N-channel devices, the enhancement mode MOSFET is restricted to operation in the first quadrant, and the JFET is typically restricted to operation in the second quadrant. There are some exceptions, but for the most part, an N-channel JFET operates in quadrant 2. Now let's take a look at a particular depletion mode MOSFET. I chose the LND150. This is a pretty common, inexpensive depletion MOSFET designed to be used in low power, linear, and switching applications. Here's the schematic symbol. We can see it's got a parasitic diode from drain to source, but normally that's reverse biased and we can ignore it. Here's the pinout for the actual transistor. And I sat down in the lab, took a bunch of measurements, and these are the curves that I came up with that represent the typical device. It's got an IDSS of about 1.7 milliamps. VGS off is negative 1.5 volts, VP is positive 1.5 volts, and GMO is about 2.3 millimos. And remember, for a depletion mode device, GMO is equal to 2 IDSS over VP. All right, now one thing I want to point out is that these parameters are extremely consistent from one device to the other. I picked 10 random LND150s to do measurements on, and they all came up pretty much right on the money with these values. And that's one of the nice things about MOSFETs, both depletion mode and enhancement mode, is that their parameters are very, very consistent. Unlike JFETs, which can vary all over the place, these ones are very tight. Now, of course, bipolar transistor parameters vary a lot, but Because of their operation, we can ignore those variations in most cases. But again, as far as enhancement and depletion mode MOSFETs go, their parameters are very, very predictable, and that's really a nice characteristic of these devices. Now, because we can operate the depletion mode MOSFET with negative or positive VGS, this allows us to use a really simple biasing arrangement where we apply a VGS of 0 volts. That results in an IDQ of IDSS. It puts our Q point right here, and this is called zero bias. Now, neither JFETs, bipolar transistors, or enhancement mode MOSFETs can do this. So this is one of the nice advantages of the depletion mode MOSFET, this zero biasing option, and that's what we're going to look at next. All right, here's an example of a zero biased common source amplifier. It's about as simple as we can get. The DC equivalent, remember, we obtain by opening all coupling and bypass caps. So VGS equals 0 volts, ID equals IDSS, and the transconductance equals GMO. Over here at the AC equivalent, we've combined RD and RL into an equivalent R prime D. And again, everything is pretty straightforward because there's no source feedback. The voltage gain is negative GM times R prime D, and of course GM equals GMO. So let's just go take a look at an example problem here. And we're going to use an LND 150 IDSS 1.7 milliamps, VGS off negative 1.5, VP is 1.5 volts, and GMO 2.3 millimos. All right, so this is really simple. IDQ equals IDSS, so that's 1.7 milliamps. VGSQ is 0 volts. VDSQ is going to be 1.7 milliamps times 5600 ohms subtracted from 15 volts is about 5.5 volts. Our transconductance is GMO, so that's 2.3 millimos. The input resistance is the gate resistance, 1 megohm. And the voltage gain, AV equals negative GM times R prime D. R prime D is 5.6K in parallel with 2K. Let's see what we get here. 5.6 plus 2 equals about 1.47. Let's call that 1.5 K ohms. All right. So this is about 1.5 K ohms. So our voltage gain then is 2.3 millimos times 1.5 K ohm. And notice the upside down omega and the omega cancel. Mos is the reciprocal of resistance, and this is resistance. So voltage gain is dimensionless here, as it should be. But let's see what we get. Okay, that's 0.0023 times 1500 is a gain of negative 3.45. Let's just call it negative 3.5. So it's not a very high gain device, similar to the JFET in gain. The current gain, remember, is equal to AV times RN over RL. So we've got, let's see, AV is 3.45. We'll just leave it at that, times 1 meg divided by 2000, and about negative 1725. Let's just call it negative 1700. And of course, power gain is the product of voltage gain and current gain. So we've got 1725 times 3.5. Power gain's about 6,000. Okay, so not too bad. All right, now I've built the circuit and did some measurements, and I'm going to show you those next, okay? So let's go on down to that page, and here we go. Okay, I've carried my theoretical values over here and written my experimentally measured values in blue. The drain current came out right on the money, 1.7 milliamps. Of course, VGSQ is 0 volts. And my VDSQ was 5.3 volts versus 5.5, probably due to resistor tolerances more than anything. And the voltage gain actually came out a little bit better than expected, which is a little bit unusual, but very close to the predicted value. As we can see from the scope capture here, my input voltage was roughly 100 millivolts peak to peak, and that produced an output of about 382 millivolts peak to peak. And it appears pretty clean, not much distortion. I turned the input up to about 3 volts peak to peak just to send it into clipping, and we have an output of about 5.3 volts peak to peak. The top peak is reaching about we're 1 volt per division, so that's about 2.5 volts on the positive peaks, and negative 2.5 on the negative peak. So we've got pretty symmetrical clipping. It is a little bit asymmetrical in shape, but not too bad. So this is a fairly well-centered Q point here. You can calculate these values on your own. I'll leave that to you as an exercise. And it's a pretty decent amplifier, very easy to design and set up. So you know, that's probably the most common configuration for a Class A small signal amplifier using a depletion mode MOSFET. So let's go do another example. All right, here's our circuit. We're using the same FET. Now we're using source feedback biasing. So to determine the Q point, we're either going to have to use the quadratic formula or use a graphical solution technique. If you use the quadratic formula, the constants work out to be A equals 82.28, B is negative 1.748, and C is, of course, 0.0017. And when you grind through all the numbers, you end up with a solution of ID is either 20 milliamps, and it's not that, that's the extraneous solution, or 1 milliamp. And 1 milliamp is the correct solution here. That's subtracting the radical in the quadratic formula. So 1 milliamp, that would give us a VGSQ of negative ID times RS. Remember, VGS equals negative ID times RS. So 1 milliamp times 330 ohms is 0.33, so VGS should be negative 0.33 volts. All right, now using the graphical approach, I've already got it up here. Here's our transconductance equation, IDSS times 1 minus VGS, that's X, divided by VGS off, negative 1.5 volts, squared. And our green line for ID times RS is negative X, which is VGS over RS 330. And our solution is about 1 milliamp and negative 0.34 volts. Okay, and we got 1 milliamp, negative 0.33, just rounding error. So we're in good agreement. All right, our VDS at the Q point, VDSQ equals VDD minus IDQ times RD plus RS. Let's plug those numbers in and see what we get. Let's see, 5600 plus 330 times 1 milliamp is 5.93 volts. So 10 minus 5.93 is, let's round that to 4.1 volts. So VDS should be about 4.1 volts. Our transconductance, GM, is equal to GMO times 1 minus VGS over VGS off. And let's see, whoops, let's move this over here. So VGS is, I'm going to use positive numbers, 0.33 divided by VGS off, which is 1.5. Subtract 1, ignore the negative sign, and let's multiply by our GMO, which is 2.3 millimos. And again, ignoring the minus sign, it's about 1.8 millimos. 1.8 millimos. Now, our input resistance is approximately equal to Rg, that's 1 mega ohm. Voltage gain, well, we need to find R prime D first. R prime D equals, remember, Rd in parallel with RL. So, oh, that's a little messy. Let's see what we get here. Rd is 5.6K and RL is 2K. And that gives me about, let's say, 1.5K for R prime D. Okay, it's approximately 1.5K ohms. So let's see, voltage gain then is negative GM times R prime D. So we've got negative 1.8 mils times 1.5K. So that's going to be 1.8 times 1.5. The K's cancel and the Mos and ohms cancel, which gives us a gain of negative 2.7. Negative 2.7. Okay, our current gain, A sub I, is equal to AV times Rin over RL. So we've got, let's see, 2.7 times 1 million divided by 2,000. Oh, not 20,000, 2,000 is about 1350. Let's just call it 1300, negative 1300. And lastly, our power gain, A sub P, is AV times AI. So it's going to be 1300 or 1350 times, what was our voltage gain? 2.7, about 3600, let's call it. Okay, so our power gain is 3600. Again, pretty decent current gain and power gain. The voltage gain, not too high, but this is not a high transconductance MOSFET. Okay, so this is about what we'll get from this thing. All right, so now let's go take a look at our experimental results. All right, here's our circuit. I've carried across the theoretical values we calculated. The experimental values shown here in blue. We got just slightly less drain current than predicted. Also, our VGSQ was just slightly off, pretty close. VDSQ, a little bit higher, 4.2 volts versus 4.1. And our experimental voltage gain was a little bit better than expected at negative 2.9 versus negative 2.7. So let's look at this first scope trace here. We've got an input of 100 millivolts peak to peak. We get an output of 292 millivolts peak to peak. So there's our voltage gain of negative 2.9. And it looks like a pretty clean, undistorted replica of the input, just inverted. Now I bumped the input up to 500 millivolts peak to peak, and our output increased to 1.39 volts peak to peak. And it still looks pretty good, but if you look closely at the peaks, notice that the top positive peaks are a little bit more rounded than the negative peaks. They're a little bit sharper down here, and that's due to the transconductance of the MOSFET varying as our Q point moved on the transconductance curve. That's an interesting topic that we're going to discuss in great detail in another video coming up soon. We'll compare this kind of distortion for all the devices, BJTs, JFETs, and MOSFETs, and we'll get a little bit more in depth on that, and I think that's going to be an interesting topic coming up. And finally, I increased my input to 2 volts peak to peak, which overdrove the amplifier pretty significantly. Our maximum output voltage works out to be about 1.6 volts peak. We're at a half a volt per division on the vertical axis, so this is about 1.6 volts, and the negative clipping level is about negative 1.8 volts. So we've got a pretty well-centered Q point here, and this is not a bad amplifier. Now, before we move on to the next slide, I'd like you guys to calculate the clipping points for the amplifier and see how they compare to these experimental results. And also determine the voltage gain with the source bypass cap C3 removed from the circuit and see what you get for that as well. All right, now the next example we're going to look at, we're going to use a different MOSFET. We're going to use the DN2535. This is another popular, inexpensive device, but it's designed to be used at much higher currents. IDSS is 150 milliamps for this one. So that means right off the bat, we can't use zero biasing in our circuit. I mean, an IDQ of 150 milliamps would just be crazy for the applications we're looking at. So we're going to run it at a much lower current than this, and that means we'll be way down near the vertex of its transconductance curve. All right, and that's going to cause some interesting things to happen. But before we get to that, our VGS off is negative 2.9 volts, VP is positive 2.9, and it's got a relatively high GMO of 103 millimos. Now, for this circuit, to calculate IDQ, of course, we're going to either have to use the quadratic formula or a graphical approach. And I put a little red asterisk here because when you do the quadratic approach here, this is one of those weird cases where B squared and 4AC are very, very, very close, and you have to calculate both of these values out to like 10 decimal places to make sense out of this equation. So this is something you have to watch out for. Sometimes that happens, and that's happening here because we're operating very close to the vertex, and our ID times RS line is very horizontal down there. So, it's something to watch for, but it'll be interesting to see what happens if you try this approach and see what you come up with. I'm going to use the graphical approach, and here it is. I've entered the parameters for the transconductance equation, IDSS 150 milliamps, VGS negative 2.9 volts, and here's the parabola. And then it's negative VGS over RS 470, and here's our solution. We get a drain current of about 5 milliamps and a VGS of about negative 2.37 volts. Okay, so let me write those down. Negative 2.37 volts and 5 milliamps. Had to write this one first because I'd probably forget it as soon as I read it. All right, but anyway, now VDS, of course, is equal to VDD minus IDQ times R sub D plus RS. And let's see what we get here. Okay, RD is 1500 plus 470 times 5 milliamps, 0.005 is 9.85, and we'll subtract 15. Ignore the negative sign. So we've got a VDSQ of about 5.2 volts. All right, our transconductance we know is GM equals GMO times 1 minus VGS over VGS off. All right, so let's see what we come up with here. VGS is 2.37. I'm ignoring the negative signs. Divided by 2.9. We'll subtract 1. ignore the negative sign, and multiply that times GMO of 103, and that gives us about 18.8 millimos. Okay, ignore the negative sign there. So 18.8 millimos. Our input resistance again is Rg, that's 1 megohm. And now let's figure out our R prime D. That's an easy one. R prime D is just 1500 divided by 2, or 750 ohms. So our voltage gain, AV, equals negative GM times R prime D. And that's, let's see, 0.0188 times 750 is a gain of about negative 14, let's call it. Okay, negative 14. Our current gain, of course, is negative 14 times Rn over Rl. So Rn is 1 meg divided by 1500 times what was our gain? 14. So now we've got a current gain of about 9300, let's call it negative 9300, just rounding it off. And finally, the power gain is going to be 9300 times 14, about 130K, let's call it, okay, because I'm rounding off like crazy here all over the place. We'll just say it's about 130K. Pretty high. All right, now let's go on over and take a look at our experimental results, because I built this one too. All right, here's our circuit and our experimental results. As you can see, the measured values came out very close, especially at the Q point. Our voltage gain was actually a little bit better than we expected, and that's usually a good thing. Coming over and looking at our first waveform pair here, we've got an input of about 208 millivolts peak to peak. The output is 3.66 volts peak to peak. That's where we got our gain of negative 17.6, and everything looks pretty good. Now if we bump V in up to 500 millivolts peak to peak, then we notice that we start getting some distortion. The top of the waveform is kind of squashed and the bottom is stretched. This is very characteristic of amplifiers that have no negative feedback. Both BJT, JFET, and MOSFET type amplifiers exhibit this kind of characteristic. And again, we'll talk about this very soon. And finally, when I drive it into clipping by applying a 1 volt peak to peak input, I get a positive clipping point of about 3.8 volts and a negative clipping point of about negative 5. So we don't really have a centered Q point, but it's not bad. We do get a pretty decent output swing from this amplifier. And that concludes today's video. Hope it wasn't too boring or repetitive for you. But that's it for today, and I'll see you guys next time around.